We're going to return to calculus now and this idea of rates of change, which we had a bit of a look at before. Now, sometimes we need more than one rate and we have to link them together to come up with the overall rate that we're looking for to get it in the right format. Basically, it comes from our chain rule, implicit differentiation, call it whatever you want, but that idea. If I want to find dy dt, I could find dy dx and multiply it by dx to t. Because rates we can think of as fractions and the dx's, if you like, cancel. Let's look at a couple of examples. We have a block of ice, an ice cube, edge 10 centimeters long. It's melting, its dimensions are decreasing at the rate of 1 millimeter per second. We want to know the rate of change of the volume when the edge gets to 5 centimeters. So what rate at that point is it decreasing? So I draw myself up a little picture there. Okay, that's a cube. Side length I'm calling x. We want to find dv to t. What's the rate of change of volume as time progresses? But what do we know? What rates have they given me? Well, they've told me that the length of that side is decreasing at the rate of 1 millimeter per second. Now, we've got to be careful with our units here. Notice they told us 10 centimeters long, but they've quoted the rate as 1 millimeter per second. So therefore, I've written it as 1/10, not 1, because 1 millimeter, of course, is 1/10 of a centimeter. It's decreasing, so I've made it negative as well. Now I want to find dv to t. I know dx to t. So ideally, if I could come up with a relationship between v and x and differentiate that and get that rate, we can come up with a formula. So how do we link volume and the side length? Well, that's just the volume of a cube, which we know would be x cubed. Differentiate that with respect to x, and we get 3x squared. We can now complete our little formula. So dv to t will be 3x squared times minus 1/10. I can tidy that up and I have a formula. It's in terms of the side length, which is good because that's the information they've given me. We want to find the rate the volume is decreasing when the edge is 5 centimeters. So essentially now it becomes a substitution question. So when x equals 5, what is dv to t? Substitute 5 in, and we end up with negative 7.5. We answer the question, we just don't leave it as minus 7.5. So answer the question, there we are. Okay, the volume is decreasing, the negative tells me it's decreasing, at a rate of 7.5 centimeters cubed per second. Let's do this one. A vessel is in the form of an inverted cone, vertical angle 90 degrees. The depth of the water is x centimeters. Find the volume of the water. So again, I'll draw myself up a diagram. It's an inverted cone, and I've just drawn a blue line in there to represent, oh well, there's the level of the water. They said the depth of the water is x. We want to find the volume. Okay, essentially the water forms a cone as well. Volume of a cone, 1/3 pi r squared h. Well, we've got the h, we need to work out the radius. Well, if I just redraw that triangle, because that angle there is 90 degrees, when I chop it in half I get 45 degrees, so I actually have an isosceles triangle there. So the radius is actually the same as the height. Volume 1/3 pi r squared h then becomes, eventually, there it is, 1/3 pi x cubed. Okay, we've got an expression for the volume of water. Part B. Water's getting poured in at a rate of 0.2 centimeters cubed per minute. Find the rate the depth is increasing when the water depth is 4 centimeters. So we want to find dx to t. What's the rate of change of that depth? Okay, at this stage we have a link between volume and x. So we can find dv dx. They've also told me dv to t, that's 0.2 centimeters cubed per minute, so I know dv to t. Let's work out dv dx. Volume we said was 1/3 pi x cubed, so dv dx pi x squared. Substituting in, we can come up with a formula. We want, when x is 4, substitute in 4, and well, 1/80 pi would be the exact number, and I'll just leave it like that. I mean, we can go to a calculator and get an approximation, but it's increasing at a rate of 1/80 pi centimeters per minute. Sometimes you need more than 2, and I think this one here we're actually going to use 3 rates to come up with a solution. So a spherical bubble, expanding, volume is increasing at a constant rate, 70 millimeters cubed per second. So we're just blowing a constant amount of air into a balloon, maybe it's something like that. What's the rate of increase of its surface area when the radius is 10 millimeters? So we want to find ds to t. They've told us dv to t is 70. Okay. I've got dv to t, I want ds to t. I don't actually have a formula that links volume and surface area. So this is why I'm going to need two, because I can find a formula that links surface area and radius. I can also have a formula that links volume and radius. So through these three different rates, I can come up with a formula. Let's find some of that information then. Volume of a sphere, 4/3 pi r cubed. Differentiate that, we get 4 pi r squared. Okay, I have dv dr. Coincidentally, the surface area is 4 pi r squared. Surface area of 4 pi r squared, so ds dr becomes 8 pi r. Substituting all of that in, I get 70 times 8 pi r times the reciprocal of 4 pi r squared. I simply get 140 over r for a formula for ds to t. So what that's saying is the rate of change of the surface area is inversely proportional to the radius. Just imagine blowing up a balloon. Think about that. As you're blowing up a balloon, that surface area changes at a slower rate as the radius gets bigger. Well, you think about it. You've got a balloon, there's no air in it. So the first thing, it expands really quickly. But as you blow more air in, it goes out just a little bit more and a little bit more and a little bit more. So yeah, that makes sense. Let's substitute in 10 and we get 14. So there's our answer. We know when it's 10 millimeters, the surface area is increasing at a rate of 14 millimeters squared per second. So 16a, we'll look at some of these rates of change questions which will involve more than one rate. We've got to link them together to come up with a formula.